Okay, so first of all, quick introduction. My name's Alex Bennée. I work for a company called Linaro. So I'm a member of the virtualization team there, so I mostly work on QEMU's emulation abilities with the occasional side into KVM. So my primary interest is having a decent emulation of ARM systems. So, why vectors? So a lot of the activities we take for granted in modern computing are enabled by vector processing. Things like video playback, audio processing, and 3D modeling involve large amounts of data processing, which have been enabled by the evolution of modern processors to cope with these computationally heavy workloads. Vectors can be leveraged in any algorithm that exhibits data parallelism. So, for example, in audio processing, if you want to attenuate a signal, you might want to apply an identical transformation to each and every sample. So the results of each calculation are independent of the samples before and after, and they make a good candidate for being vectorized. So let's talk a little bit about how vectors work in CPUs. Let's start with the vector register. So this is a wide register that contains multiple elements, usually referred to as lanes. So in this example, we have a 128-bit vector holding 4 32-bit values. Now, why is this useful? Let's have a look at an example vector operation. So this is a vectorized add. So we have a single instruction to add the contents of Vn and Vm together. And importantly, we are processing each lane separately. So this is why these instructions are often referred to as single instruction multiple data, or SIMD instructions. By saving the cost of the extra instruction decode for each operation and usually having multiple arithmetic units inside the CPU, you get a simple level of parallelism in your processing. Another thing to note about vector registers is they support multiple sizes of operations. So with a 128-bit vector, you can process 2 double precision floating point numbers at a time. However, if the final precision of your calculation isn't required to be so high, you can trade speed for accuracy and process twice as many single precision numbers. This is the reason for a lot of the drive for half precision support, because you can increase your throughput again for the same memory bandwidth. Sorry, apologies for that. So other examples of highly data parallel tasks include things like general matrix multiplications. So you may have come across this in 3D work, where you need to apply a matrix transformation to every pixel or vertex of your model. You see similar transformations in AI and machine learning workloads. Also, scientific data processing and simulation often have parts that are highly data parallel. So perhaps it's time we took a look at the history of vectors in computing. So vector processing has been core to a lot of supercomputing tasks since the early days. Can anyone name this machine?
Yeah,
Cray, that's right. It's the Cray 1. It was a powerful machine of its time. It was one of the early supercomputers. It was built only a few years after I was born. So even though it clocked in only 80 megahertz, it could achieve 250 million floating point operations a second. And this was mainly due to its vector-based design. It had 8 vector registers, and each of those vector registers was capable of holding up to 64 64-bit elements. So this allowed it to execute the same floating point operation across multiple elements of the vector register, giving it its comparatively high speed for the time. So since the 1970s, vector pipelines have been integral to many of the supercomputers of the last 40 or so years. As you can see, there's been a steady growth in the number of floating point operations a second they could achieve. By the turn of the millennium, processor nodes were running at around about 8 gigaflops. So this is the last one on the slide, the NEC SX6, which had 8 vector pipeline units. Now, each of these pipelines could have up to 72 256-word vector registers. So this gave it a total processing power of about 8 gigaflops per processing node. But even with this growth in power, supercomputer engineers had started to network nodes together to cope with the increasing demand. Next quiz question. Can anyone name this machine? So this is the Earth simulator. It was built out of 640 of those SX6 compute nodes, and it had about a total of 5,000 vector processors. So gave it, for its time, a pretty respectable performance of 35 teraflops. It spent most of its time running global climate models and solving various geophysics problems. And it held the record for the world's fastest supercomputer at the beginning of the millennium from 2002 to about 2004, when IBM's Blue Gene exceeded it. So this is all very nice, but in the 90s, these vector processing approaches were starting to appear on workstation CPU architectures. One of the first was Intel's MMX instructions. These are sometimes known as the multimedia extensions because media processing was one of the first workloads these extensions were designed to accelerate. It was capable of treating each MMX register as a single 64-bit number, or two 32-bit numbers, or four 16-bit numbers, or even 8 individual bytes. So the original MMX only supported integer operations, and initially most of the code that took advantage of it was supplied by a library routine of common helper functions supplied by Intel. But most of the workstation CPUs now have vector extensions. So even though they're nominally scalar architectures, although superscalar tries to stretch that a bit, they've all added vector processing units. Spark was early with its VIS, or Visual Instruction Set. MIPS has MDMX, PowerPC is Ultivec, and for ARM there's Advanced SIMD and Neon. AMD were the first to introduce floating point operations with their 3D Now extensions, and now pretty much all modern SIMD instruction sets support at least single and double precision floating point. As time has gone on, the vector sizes have also grown. So in the x86 world, for example, the first expansion was SSE, which doubled from MMX's 64-bit registers. The current iteration is AVX512, which unsurprisingly is around 512 bits in length. As you can see, that can do 8 double precision operations or 16 single precision operations all the way down to 64 byte operations at a time. ARM has taken this to its logical conclusion. They've introduced the ARM Scalable Vector Extensions. So this introduces vectors that are up to 2 kilobits in length, along with a bunch of novel instructions that allow you to utilize these vectors without actually having to hard code the number of lanes you use at a time. So the idea being that the same code that can run on your phone, which might implement a small total vector length, can also run on a supercomputer with larger vector sizes, and you get an automatic performance boost without having to rewrite your code. So let's take a look at how this applies to our handling of vector operations in the tiny code generator. So the process is relatively simple. On demand, we take a block of machine code from the target, and it's converted into an intermediate form, which we call TCG ops. And then from those TCG ops, we generate our JITted code. This is a little fragment from a benchmarking utility I wrote for testing out vectorizable kernels. It's very simple. Hopefully everyone can understand what it's doing. It simply works its way through an array of bytes and XORs them together. Now, let's have a look at the assembly that this generates. Now, don't worry about taking it in for now. I'm going to go through it in a moment. But first, let's quickly review how register aliasing works. So, as I mentioned before, you have multiple sizes, but it's not unusual for the vector registers also to be aliased to the existing system registers. So in the ARM case, it's the floating point registers, the Q, which stands for quad, and D for double. There's also a S for single, alias with the vector registers. I'm just mentioning this so when you see QN being set up, it's the same as loading it into the vector N register. So let's go through the assembly step by step. So first of all, we need to load the data from the array. So we're loading 2 quad words at a time, one from our A pointer, one from our B pointer. They're both indexed by the X0 register. Then we do the EOR. Now the important thing to notice here is we're doing 16 bytes of XOR at the same time. Finally, we save our result in the destination pointer, again indexed by X0. And then finally, we loop round. So as you can see, we're doing 16 bytes at a time. So let's have a look at how these instructions get broken down into TCG ops. So the first one I'm going to look at is the load operation. So the LDQ register is loaded. LDQ operation is loading 128 bits from memory pointing at by X21, indexed by X0. So there's a couple of steps we need to go through. First of all, we need to calculate the address of the load, and we do this by adding X21 to X0. The next step is to do the load from memory into one of our temporary registers. Now, as you can see, we're actually doing two loads here, so it does mean we also need to calculate an offset for the second load to get the right place. And then finally, we store these two temporary registers into QEMU's CPU register file. So this is basically a fixed offset of the per CPU environment structure, which the generated code can access directly. Now, the main takeaway you need to take from this is we're doing two 64-bit loads and two 64-bit store operations to cover the whole vector. Why is this? Well, currently TCG is only really aware of two things. And that's 32 and 64-bit registers. The remaining two are actually just aliases that depend on the pointer size of the emulated guest and the host. So as a result, all the vector operations have to be marshaled in and out of, in this case, 64-bit registers. So we have a look at how this affects the actual logical operation. So this is the EOR operation. The computation is doing an exclusive OR of 16 bytes from V0 and V1 and storing the result in V0. So again, first we need to load the values from our environment structure into the temporary registers. So here we load the first half of V0 and V1. Fortunately for us, XOR is a bitwise operation, so there's no particular reason why you need to do this a byte at a time. So we emit a single 64-bit XOR here. And then we do the same for the second half. And finally, we store the results back into the CPU structure. Now, for this example, performance isn't too bad. In my test case, QEMU actually outperforms the native run. Now, this is a little unfair because my development box is a fairly modern x86 and the AArch64 reference platform was a underclocked early development board. But perhaps I'm worrying too much about the impact of vectors. So let's look at a slightly more complex operation, one that we can't lump all together like a bitwise operation. So this is almost identical to the previous test, except instead of doing an XOR, we're multiplying two single precision numbers together and storing the result. Let's look at how the guest compiler vectorized this code. As you can see, the main structure of the loop is identical to our first example. But now you can see we're doing 4 single precision multiplies in our 128-bit vector. Let's look at how that gets broken down in our translation. So, the fmul instruction. First of all, we need to calculate the address of the FP status register. So this is where we store things like exception flags. Then we need to load the two source values from our CPU environment. The next thing we do is we call the VFP muls helper function. And then finally, we store the result back. And then we have to do it 3 more times. So this isn't too bad for 4 multiplies, but it's going to add up soon if you're doing 16 multiplies on an AVX 512 vector, or potentially on SVE, you might have to do 64 of these in a row. So let's have a look at the helper function. Now, this is a helper for VFP muls. It's actually simply a wrapper around QEMU's internal copy of softfloat. Why are we using softfloat instead of code generation? Well, in the pre-TCG days, QEMU templates did rely on the compiler-generated floating point operations. However, it quite often got it wrong. There were enough ambiguities. There are enough ambiguities and options in things like rounding behavior and exception behavior that made it hard to directly map the behavior of one instruction set to another. So as a result, we switched to softfloat, where it's easier to explicitly control the behavior of the system. There's also a small penalty you need to pay for loading each element up and marshalling it into the CABI, because obviously you need to call a C function. So now I've recapped the existing code generation, let's look at the work that we've done to improve the handling of vectors in TCG. Now, there have been attempts at better SIMD instruction behavior before. So most recently, there was Kirill's work posted at the beginning of the year. So it added the concept of a 64-bit and 128-bit vector register, along with a new memory operation for accessing 128 bits at a time. Now, it was only a proof of concept, so it simply dealt with the integer add operation, but early benchmarks were promising. Kirill saw a 10% boost in processing for X264, which is a media codec, just from being able to use the larger registers to load and store stuff. And he also saw a speed increase on simple loops. However, one problem that might become apparent from this work is you have to add quite a lot of extra TCG operations for each vector size you support. You end up adding operations for each combination of lane and vector size, and that gets tiresome quite quickly. So I'm just going to quickly go through the design principles of the current work. So the first thing we want to be able to do is easily support multiple vector sizes. So as you saw from the earlier slide, there's been a steady growth in the size of vectors, and it's not a trend that's likely to stop. Even SVE's 2K large vector support leaves plenty of space in the architectures to expand it later. Secondly, helpers are still going to dominate floating point processing, and it's likely to do so for the foreseeable future. So any interface that therefore the interface that we present to helpers should be as efficient as possible. And finally, even though we're going to be mainly calling helpers for floating point, there are operations that can be dealt with in generated code, and we should maintain the ability to do that. So the current work is Richard Henderson's patches, which were posted about a month ago, and they take a slightly different approach to Kirill. So we've introduced a new type called TCG Vec. So this normally represents a pointer directly into the guest CPU register, so directly into the M structure. Most importantly, it's a size-agnostic representation. I'll show you how that works in the next slide. So while most of the users of this interface are likely to be guest architecture specific, it does also introduce some universal ops in the core TCG code. Now that's done with a mixture of generic helpers, which work like normal helpers do, but it also allows the generation of code if we know the back end can support efficient code generation. So let's look at a helper first. So this is the default helper for a vectorized XOR. Now you can see it's size agnostic, as in there is no fixed size that it needs to process. What's actually happened is the size of the vector is passed in one of the parameters to the helper. It's encoded in that 32-bit desk field. So one nice side effect of this is now the compiler knows that we can be going over a whole number of XORs. It can vectorize the helper. So let's just have a quick look at the inner loop of the vectorized helper. So this is on my x86-64 host. So even though it's a different instruction set, hopefully you can see there's some similarities in the code. So the main difference is because x86 can do an XOR straight from memory, it's not loading two things into register. But hopefully this will run as efficiently as possible. So although you might pay a penalty for setting this up and calling a C function, at least for very long vectors, the helper function will run quite efficiently. However, for simple operations, I think we can do better. So let's just remind ourselves of the IR that we generated under the old scheme of things. We end up doing 8 operations for our 16-byte XOR. Let's look at the IR that we generate with the new TCG Vec work. So as you can see, this is already a more compact representation of what's going on. Importantly, each operation has enough information encoded in it that the backend can also generate the most efficient code possible. So this is the SSE code that it generates on my machine. So now you can see we've got quite a close mapping for the EOR. We're using a 128-bit SSE XMM register to do the XOR for the 128-bit guest register. So let's see what amazing performance changes we have from this work. Well, okay, that's a little disappointing. In most of the test cases, the TCG Vec-enabled code runs slower than the existing TCG code. But it does look as though one of the tests is running a little bit faster. That's the bitewise bit fiddle test. So let's have a quick look at what that's doing. So the main difference here is bit fiddle is doing more logical operations in a loop. In fact, this is exactly the reason that Seymour Cray introduced vector registers back in the 70s. So his observation was, although the process of loading registers from memory was expensive, when you chained operations together, you could get that performance back. This might be clearer if we look at the guest assembly. So don't worry about following all of this, but the key thing to note is that we're doing more calculation operations in each loop, and therefore more operations in each translated block. So this makes sense given the target workloads for these SIMD instruction sets. They're aimed at processing large streams of data. So as a result, the CPU designers have sacrificed latency in favor of throughput. So executing one SIMD instruction per loop is really going to be the worst case. Is there a way we can test this? Well, maybe it's time for me to declare that I am in fact a Gentoo user. So let's recompile all the tests with funroll loops. So for those of you not familiar with this compiler flag, this basically instructs the compiler to unroll the loop as much as it can and do as many operations with the registers set that it has before it goes round again. Now, as you can see, the picture looks a lot better. So while the existing TCG code has also seen an improvement, the vector code is a lot closer in performance. And importantly, it now beats the existing code in 2 of the test cases. So we've still got a little bit of a distance to go, but let's talk about what else we can do. So the first thing that needs improving in the current work is the load and store of vector registers. In this case, we're still marshalling our loads through 64-bit registers to get them into the CPUM structure, even though we're doing 128-bit operations once we get there. Secondly, we need to make better use of the temp registers. So while we still have to store interim results into CPUM for correctness sakes, we're not currently reusing the register for computing further chained operations. So we end up loading from CPUM, doing the operation, storing back, loading from CPUM, and going back. So we can make that a little bit more efficient. Now, our main focus for this work is going to be supporting the upcoming SVE work. So once the prerequisites have been merged, expect to see more work building on this framework as we implement SVE. Others are, of course, welcome to look at using this work for other architectures. So, in conclusion, TCG-Vec offers a flexible solution for representing vectors of various sizes. For the front ends, the main benefit is it results in better TCG op density over having the existing marshalling approach. Now, while helpers are still going to dominate for floating point workloads, the richer interface to the back end does allow us to vectorize integer and logic operations. And we should see the performance benefits with heavily vectorized guess code. So with that, I'll open the floor to any questions. Go.
Can you think of a reason why it took? Hi. Can you think of a reason why it took CPU vendors so much time to add size agonistic instruction sets?
Why it took vendors so long to add them?
I mean, why does Intel add generation after generation rather than one generation of size agonistic vector?
I could only hazard a guess, and I suspect it's because the early workloads for workstation CPU architectures were targeting specific test sets, which are usually multimedia processing, where you've got a limited size. I mean, as you can see, even with the 2K vector in SVE, that's actually a fair way smaller than some of the sizes of vectors that the supercomputers were doing, which are obviously geared towards doing much higher throughput data crunching. But it's going to come. So, I think the SVE architecture itself is part of ARM's strategy to, tackle everything from the mobile chipset up to high-performance computing. So that's why they've come up with this flexible approach.
I just want to make sure both x86 and ARM use the same IEEE floating point format.
Almost. So, well, okay. So most modern CPU architectures tend to follow IEEE semantics for their operations, but the IEEE standards a bit lax about generally what rounding modes are enabled by default and what exceptions are generated by default. And that's before you also add in things like extended floating point format. So on ARM, you have an option of either using IEEE format or using ARM's extended floating point format, which obviously needs to be
the
handled
helper
separately.
function deal with that?
Yes, because the helper function does it all manually by hand. It unpacks the exponent and the significand and does it all properly and then fits it all back. So that's why we use the helper functions. I would like to live in a world where we could actually generate direct code, but it's going to be hard. I think it's easier if you're building a single architecture to single architecture translator, because then you've got a lot more control over what you're running on. Obviously, one of the benefits of QEMU is we support so many front ends, and all of those front ends can run on any of our back end code generators. So, any more questions? Okay, well, I think I'll rush through that too quick. But,